Hello, everyone. Firstly, say thank you to the organizers of the conference. Thanks for having us here. And especially thank you for all the technical presentations and all the industry talks. It's been definitely an amazing experience, first time in this conference for me, and definitely hope it's not the last. So thank you. Right, so I would like to take this chance to talk a bit about the recent development we're doing on the OTFT PDK. Our target is to achieve low voltage flexible logic circuits on plastic substrates. So just to introduce you a bit to the company, I'm going to talk a bit about our background. So yeah, as you can see in the map, we're a bit spread. We're actually an American registered company. So we're in the US and the US Stock Exchange. But you can see our facilities are a bit global. So we've got our manufacturing facilities here at Sedgefield, which you can see in the United Kingdom at the top. That's where I'm based. We got access to CPI prototyping facility over there. For those of you that don't know the UK, that's very much north of the UK. That's pretty much Adrian's Wall, as north as it gets. And then you got Scotland. And then we got some headquarters in Smartkem, which are basically based in Manchester. This is where we do all of our chemistry, formulation, R&D development, which in conjunction with the process development makes our prototyping. We also have technical support, business development in Taiwan and Tokyo. And we've got partnerships with companies like Linkcell, which you can see are based in China. And they also aid with the engineering support and business development. So our prototyping and manufacturing readiness, you can see we can produce materials from kilogram scale, that's based on solid materials, down to small samples. We can also produce a range of package sizes. We can get from a couple 100 milliliters if you want to do a small scale integration or prototype. We can also scale up to several liters. We've got access, as I mentioned, to the Gen 2.5 prototyping facility, which you can see in some of the pictures here below. And that helps us do our qualification of process development. We have basically an OTFT compatible technology in a variety of source drain electrodes. So we've managed to achieve good performance with copper and moly. And that's a short channel, which is quite important, as a lot of you will know. And we are currently at 75% of the mobility of gold source drain electrodes. We also have scale up to a Gen 2 class facility through our partners, strategic partners. And then we've got a slot die coating formulations readily available for scale up. All of this enables us to do rapid prototyping. And we also have a direct lithography tool, which you can see in the middle picture, which avoids the use of mass sets and long turnover times. So OTFT, as you can see, and many of you will know, OTFT is a proven, robust technology, thin film transistor technology. You can see a number of tests here. The first one, you can see a ball dot test with a 200-gram acrylic directly into the OTFT structure without any problems. Here you can see some flexes with a 0.5 millimeter radius. And then you can see 100,000 flexes at 5 millimeter radius. And that's not in the neutral plane, if some of you are wondering. You can see the last one is a bit more crude, but it kind of works. So no stress. Yeah. Okay, so robustness of OTFT, we can say that the organic semiconductors really bring the benefits of robustness and durability to the designs on flexible. You can see here in the curves, unlike some other technologies which tend to shear the gate stack, you see a deviation in the on currents. For OTFT, you don't see that, and that's over 100,000 bends. We sometimes see some hysteresis and shifting on the turn-on voltage of the devices. But to be honest, all of this is done in the light conditions. So a lot of this stuff could be external factors. So overall good performance there. So why choose OTFT, Smartkem's OTFT? you can see pretty much our current status of the art is development and demonstrated prototyping with e-paper, LCD, OLED, AMOLED, and recently with the growing demand for micro LED, we have been able to show some full-scale integration with micro LED. We got decent mobility at 3 centimeters square per volt second, which obviously is far away from things like LTPS, but it serves the purposes for display applications and many others. We've got a very cool 80 degrees C maximum process temperature. The reason why this is important is because it allows monolithic integration for things like micro LED, which do not like high temperatures. So you can completely avoid long, complex mass transfer processes into your backplanes if you're doing a backplane design. Our substrate compatibility, because of these low temperatures, is quite wide as well. So we tolerate a wide range of plastics and glass. We've got good current stability, and I think it's achieving the excellence now. And I think we've got excellent sort of best-in-class off currents provided by the low leakage of the gate and the semiconductors. Excellent impact resistance. So this is an inherent benefit of using organics, and we believe here we've got a bit of an edge. And bend radius, you can see it's less than 0.5 millimeters, but not in the neutral plane. Manufacturing maturity is still at the prototype stage, but we're looking at increasing our partners and working with our collaborators to get this into market as soon as possible. And we do have some single layer applications which are already seeing the market. So this is a bit of a demonstrator of some of the applications, display applications we've been looking at, just to give you an idea of what we're doing. It's a bit of a bright picture, but you can see here on this side, we've got a micro LED monolithic integration, putting out over 100,000 nits. So I actually had to bring this down a bit, completely saturates the camera otherwise. And here you can see picked and place small LEDs put onto our backplane using Smartkem's materials, and then we're using a downscale rendering software that we've made to basically drive the picture behind. And finally, on the right-hand side, you can see an AMOLED integration with an OLED with Red Display, our partners. So the main focus of this talk is actually building an EDA. So I'll start with that. Building ASICs, what's an EDA? The dream is where the designer just builds the HDL description, the hardware description language. That typically involves coding, simulation, synthesis, and performance constraints. So you got area, speed, and power typically. All of these need to be fed into the EDA tools, and they need to be personalized for a particular platform technology, PDK. This all converts into a layout, which is the final product, and that gets sent to the foundry, which gets you the chip made. So EDAs we can classify as the tools that transform the HDL description language into a circuit layout, and this is usually in two phases. We got the logic synthesis, which is HDL to gates, and then we got the physical synthesis, which is actually making those gates to layout. I think some of our colleagues have discussed this in other talks. And the PDK just simply puts that technology information together and feeds it to the EDA tools. So some of the things we were considering when choosing the way forward for us, we strongly believe there's a need to standardize some of this stuff. When we talk to our partners who we're trying to integrate the technology, in order to facilitate this adoption of the technology, we need to speak the same language, and not necessarily everyone wants to work with the detail niche of organics or organics processing. So enabling the CDA tool would provide an open more opportunities for us. And we think this is the way forward. So we've got two options. We can go commercial. So we've got things like Cadence, which you're familiar with, I'm sure, Synopsys, and Siemens, which is from a mentor, you might know it as such. High cost for some of these applications, and complex tools. So you need a lot of specialization to be able to use them. They include useful tools, simulation, verification, synthesis, test, and then you can do also sign-off and verification of your synthesis. This typically is achieved using cell libraries, and it also encourages IP development. So there's benefits to Open source is a very similar tool chain. So you've got many of the tools that you have on the commercial tools, but it's built on different algorithms. And sometimes you got options and these could be selectable, but not always you have a choice. They're based on simplified models, and they're not highly focused on graphical user interfaces, as you can imagine for obvious reasons. They offer complete automation of the process. So this is no input from the designer beyond the HDL description language. And this is usually in an FPGA style, which we kind of like, depends on your preference there. So just to describe things a bit and what this actually entails. So I've tried to group it by abstraction level. So if we start at the very top, mostly everyone is familiar with, you got the system level designs with your circuit designs, block diagrams. So this is the function of your circuit. Then you move on to high level design. This is normally MATLAB or Python if you are doing DSP or C++. And then you go behavioral design. So this is the timing descriptions or the functional design. This is where digital designers are probably more familiar and comfortable. And this is normally done in Verilog. You might be familiar with VHDL if you're familiar with Xilinx. Next down, we got the register transfer level logic. This is the complete list of registers, flip-flops, and logic functions. And so we move further down, we got the logic gate design. So again, this is the net list of the bit registers and basic logic gates, NAND-NORs, and similar to CMOS technology. And then we got in the final stages, physical gate level design, which is the net list of those cells that are available in the architecture. And we got this switching transistor level net list, which is down to a very transistor level, which is the smallest level of abstraction. So probably for most people is more familiar on the top. For us is we would be looking at from bottom up, and we are focusing from behavioral design down to switching transistor level. So we're not bothering about the system level design and high level design because we think our customers and people like you will have a better idea of what to do with different applications and designs. So a bit of a roadmap that you need to get through. You got to start off with the hardware description language, which we talked about. You can see there's some logical synthesis that we have to do to obtain these gate net lists. Okay, so once we have this gate net lists, we can actually move on to the physical synthesis and to symbolic layout. This bit between logical and physical synthesis would be your cell library. So this is what we're trying to develop in Smartkem. You'll see some examples today. And then finally, you move on symbolic to manufacturing synthesis. So this is actually converting the symbolic layout to something that is bias, tracks, metal lines, something that we can make. Okay, so what option did we go for and why? So we decided to go for the Open Road project. The reason we chose this is OpenLane is automated, offers automated RTL to GDS flow-based. You can do this with several applications. So it's not just one, but you got things like YOSYS plus ABC, Magic, NetGen, SPF extractor, all of these K layout, which we absolutely love. All of these are great tools that enable you to completely get through that process flow we've seen to get you to your GDS tape out, which is what we would make for you or the foundry would make with our materials. The flow performs full ASIC implementation steps from RTL all the way down to GDS, basically. So you can see some of the designs we've been working on. These are mainly for parametric extraction and getting some of these DRC checks, design rule checks that we need as part of the description for the PDK that will then fit the EDA tools as we discussed. So some of them were looking at smaller dimensions, transistor uniformity. We were trying some QFN paths. So these are basically to test more like ASIC devices. And then we're also doing things like connectors for reliability and humidity testing. So we can customize the layout with a quick turnover, thanks to the direct right lithography and changes chiplets, which are about 9mm by 9mm. These designs are normally 4-inch, but we got also, as you've seen before, 8-inch and 12-inch capability and Gen 2 prototyping. So some of the things we're interested, we need to define an accurate width and length, optimum width and length, for the logic gates as a mean value and accepted deviations and variations. So our logic still works, and this is important. We have achieved 5-volt logic operation using 10 times less area based on detailed OTFT inverted characterization, and we'll get into that. We've got 3-terminal or 4-terminal transistor configurations. I'll try and show you some examples. We've got an additional power rail option for the backgate voltage in a dual gate configuration. And this requires practically no current driving, but it helps us tune some of the device parametrics, which enable this 5-volt operation. We basically also have to set and define things like NOR, NANDs, auto invert multiplexers, and we are comfortable and have developed some standard P cells or parametric cells, which can make things like the D-type flip-flops and such. So we also have to validate the ranges of width and lengths, as we explained, and define the optimum standard cell topology layout. So this is a bit what we're trying to go with this Smartkem EDA toolkit. What bits do we have in it at the minute? So we've got analog design, and that includes SPICE model of our devices. We've got parametric cells, which allow for quick turnaround of small basic designs. We've got digital design, that's standard cells and timing models. And we also have transistor level modeling. As I said, this is normally done through very detailed parametric extraction through SPICE. We also have additional components being developed, such as the RC, LVS, and PEX. We've got behavioral modeling in progress, and we also have analog modeling and digital signal modeling that we're trying to do. Okay. So this is the immediate road we see to the new platform is defining a standard library. So again, we've got all these GDS files of standard cells. This is just digital, okay? So it's not easy. And then we've got technology left files. So this is all the relevant information of the metal interconnects, layers, bias, and spacings. We've got things like the left file and macro definitions of the cells and designations. And then we also have mapping, place and route, and such. So I'll move on to the process flow. So this is a standard process flow for Smartkem materials. This is a 4-metal 5-mass process that we have. You can see we start off sputtering as molybdenum, aluminum molybdenum backgate. Again, we can change these materials. We've got a range of materials available. We normally do this by photolith, but we can also do it on direct write. Then we got base layer, coating and spinning. This is normally done on glass, or you can do it on something like pen or any flexible substrate you can think of. We then pattern on top of the base layer our source string electrodes, and these are normally quite thin, so we tend to go for 50 nanometers, and then we do some wet etch on these electrodes. With the current process, we can get down to something like 2.5 micron resolutions, easy. We then do some treatments and OSC spin coating and baking. This enables us to achieve 30 nanometer OSC thickness, which is key to achieve that phase separation, which I think Nali really described effectively for those of you that saw it on Monday. And then OGI spin coating and baking. So this is your dielectric. We actually have a dual system dielectric. So we've got the OGI, which is side-top, organic gate insulator, and SRL, which is the sputter resistant layer. Everything we try and do in Smartkem with the hope of being scalable. So we look at scalability of the materials and transferability. So again, that second dielectric layer enables you to directly sputter a gate metal on top. So you can see we've got a gold gate metal on top now, which we can then pattern and etch and add some passivation on top, as you can see on the picture there. And then all we got to do is then via etch down and realize our metal interconnect. So these are the current transistor configurations that we're working on, and we've managed to get them to work reliably and stable, and that's across a whole panel, not just in one place of the panel. So we've got top gate device, which you can see. This employs no back metal, so you can imagine the previous process, but you start a source drain rather than back metal. You then have a floating backgate, which is not ideal because you don't have any control over back channel currents, which some of you might be aware of. And then you got backgate tied to source or ground. So this can be grounded if you want it, or you can tie it to one of the terminals, effectively reducing the complexity. And finally, you got the dual gate synchronous, we like to call it, or dual gate device, which is with both gates in tandem connected together. The fifth and final option we got is the one you can see on the right-hand side. This is a 4-terminal device. So we actually have the option of adding a voltage bias and modulate the transistor performance and behavior. So these are some of the performance that you can expect, or you can see this at slightly different parametric performance, but the main take here is that they're quite reliable and there's no deviations in uniformity. And again, to show that we do kind of look at that, everything we do is based on actual data. I've left a panel with an issue there, so you can see it's real data. It's got a scratch on, and we can scale this to 12-inch and 8-inch and get really good reliability. Some of the issues that you see on there, the red dots, obviously drop in yields, they actually drop in mobility, so they still work, but they're low current. So we fixed that. So everything we do has got to be scalable. This is some of the performance. So why having the backgate and why is that important? It gives us this ability of tuning the threshold voltage. This threshold voltage tuning effect, then we can use in things like inverters and logic, and we can get what would be a 10-volt operation into a 5-volt operation. The actual currents of the organic semiconductor that we produce and the transistors that we produce is extremely low. Even in the case of the 4-terminal device, you can see it's in the femtoamps. We actually had to go to our colleagues in NPL, National Physics Laboratory in the UK, because we would have spent months trying to get noise level resolution. But yeah, you can see there's absolutely no gate leakage. And likewise, you can see another example, a 10-volt VDD. So we're increasing the voltage now and trying to move the back gate. So long story short, if you want to decrease your VTO, you could apply a bigger positive backgate voltage, and you can achieve that with a 4-terminal device. So some inverter characteristics. So likewise, we did for the transistors. I've tried to pick, this is done using statistical software analysis. So I've kind of picked the worst and the normal to try and understand how much variability we got and how reliable this logic is across the substrate. So you can see some of them have got nice turn-ons. Ideally, you want for your noise margins to be high. You want it to be a 50% of VDD or close. So you got a nice range and a clear on-off, clear inversion point, I should say. So yeah, you can see it does vary a bit, but they're normally within the 5-volt operation. And what we're trying to do is to optimize this. We have several things that we're trying to do. We can either thin the gate stack dielectric, or we can also look at optimizing the process, and we're doing both. So you can see a simple inverter, very simple inverter, trying to understand why that variability that we saw before. And you got the corresponding transistors for those same devices, and we call this drive and load. So the first one is a drive, which drives a load for the inversion point, and you see the output at your top pad that we're measuring. So in this case, we're just measuring the first TFT, and we're trying to characterize what's giving us this variability. And you can see the voltage turn on all the devices is moving. And this is only 1 or 2 volts range, typically up to 3, maybe in the worst case. But it's enough at 5 volt to cause this problem. So you can see we've then done DOEs to check different ratios to see if we can, by taking more area on the substrate, reduce the voltage operation point of the devices. So you can see the green ones are lower ratio, ratio 1, and gradually, higher ratio, and then gradually decreasing down to ratio 1, which means the length and width of that device, drive device, first device that you saw in the inverter, is equal to the second, so the smallest possible size. You can see as we go to lower ratios, it's harder to get the inversion point within the 5-volt range. So we have to tune the backgate voltage to achieve that. The good news is that you can see it doesn't matter where I look in the substrate, and we test. You can see the top right-hand side one is a uniformity one. We test everywhere. So I've picked 3 in the corners to show you that there is some variability, but they're behaving the same. Moving on, some dynamic measurements. So you can see operation here are 50 kilohertz. We got them up to 500 kilohertz, no problem. But at this point, we're struggling to get accurate representation of our output signals based on the measuring equipment you use. So this is where we decided to go to the next step, which is building our own test system. For this, we use a level adaptation board, which was developed with our collaborators in University of Barcelona and CNM, which basically allows us to have some level switching and do the digital analysis of these structures. You can see an operation here. The actual board is a Discovery, which you can buy, and it's a great tool for our digital analysis. I'd really recommend it. To finish, I'll just show you some of the basic NAND logic that we've been developing. So we're trying to drive this at 5 volt, and you've got a truth table there. So the right output that we're trying to see is 0010 based on the VN and V1, VN naught and VN 1. So the two inputs that we got to our gate. You can see it's just a simple potential divider, and we're trying to tune the transistors to give us the right current at the output. So in the first chart here, you can see stable operation with the desired output sequence 0011. This is done in milliseconds, and then we can run this for hours to evaluate the stability. You can see if the backgate is not correctly tuned, there could be some stability options, and this is something we're looking into, possibly avoiding using the backgate altogether by, again, thinning that dielectric. So we're looking at getting this with basically oscillating one of the inputs, and we're keeping the other one low. So we want it to see this 000111. You can see we can do it for hours, and it will work fine, not drift. It's a bit slow. But yeah, you can see the next chart. Likewise for a NAND, you can see here the NAND 2. Skip some slide. And you can see here some data extracted with the new level switching board that we developed, which basically allows us more accurate timing diagrams and nice resolution of the data. So lastly, thanks everyone.